Okay, guys, we're ready to start. Thank you for all going to volunteer desk before coming here. Thanks a lot. And I won't spend any more words. I give the presentation to Daniel and Simon, who will tell us why all your packets are theirs.
So, hello, can everybody hear me? Okay, nice. So, we will gonna tell you something about backbone technologies and how to attack them. So, first of all, my name is Daniel, that is Simon.
Hi.
And we're some kind of old school network geeks. We fiddle around a little bit with protocol stuff and try to break things. We're working for a Germany-based security company called ERNW. And yeah, what should I say? We have fun with breaking Cisco's. Okay, let's have a little look at the agenda. First of this, we will give a short introduction into the dimension of this talk, what we will talk about and what we will talk not about. After that, we will take a look on some backbone technologies. The first and biggest one is BGP, which is used for internet scale routing and some other kind, which brings us directly to the next technology, MPLS, which is mainly used for forwarding packages in provider backbone networks. Another technology is the carrier Ethernet. This is an upcoming boom technology which is very often sold by some service provider nowadays. And after that, we will have some summary and outlook, and especially we will hold a workshop after the talk, the rest for the day, but we'll see in the end. Okay, first of all, what this talk is, we just want to reflect in a way the technologies work. We will not discuss some new, I don't know, buffer overflow or some really new technical hack. If you consider some esoteric shit, please start throwing things on us. This will wake us up. Okay, we won't have you to have a meal of laughter either. We included some bingo stuff into, but you will see on the next slide. And in the end, we want just to entertain you. That's why we brought a lab here, and we'll demonstrate some live demos on how these technologies will break. Okay, we included some kind of meat sections into the slides. So, okay, you probably know Bullshit Bingo from crypto.com. It's very funny. You can shuffle a little bit, and then you will get the security problem excuse bingo. And every time you talk to some guy in your company about security problems in the technical area, and he answers with one of these answers, you can just make a cross, and in the end, you surely will have a bingo. Okay, so the first part of this talks handle about BGP, the Border Gateway Protocol. It's this is a really old protocol, but time by time they get some new RFC out. The most current RFC is the 4271. It's from January 2006. This is for BGP4. BGP itself is kind of the glue that keeps the internet together. You know, the internet is based on three things. It's BGP, DNS, and coffee. So this is one main part which enable you to route packets through your internet. We put BGP because BGP has a really interesting trust model, and this is some trust touch talk. So we don't want to bore you with all the trust discussions. We will show some cool demos, but in the end, it all depends on trust. And BGP is a routing protocol that has a special trust model, and we will see. Okay, and BGP was kind of some heavy debates in the last years. So maybe you remember the one other thing. We will come back on that. So first, how BGP works. BGP is not an auto-detectable routing protocol, but you have to define some peers, or you have to establish relationships with your neighbors. This is done by configuration. BGP works or relies on TCP. It relies on TCP because you will see there are some security mechanisms, but they are not directly implemented into BGP, but they are moved out to TCP. Okay, so BGP won't use multicast. BGP will speak unicast to the configured peers and establish a BGP session with that peers and exchange routing information. So because it's TCP based, it's not easy to spoof. There are some ways to take over TCP sessions and stuff like that, but it's not that easy because it's TCP based. Okay, that's some main technical points. Internally, BGP announced something called NLRI, or Network Layer Reachability Information, which is the information, okay, neighbor, hello, I knew some new network and I got a route to this. Okay, on the other hand, there are some additional attributes which are defined in a lot of RFCs, probably, especially if you speak multi-protocol BGP, there are some really big attributes which are used for building the path calculation. Okay, I said BGP has an interesting trust model. This is because BGP don't use an auto-discover mechanism, but based on manually configuration, which means it's got something called intra-operator trust, which means the trust of BGP is based on the configuration of your administrator. And your administrator is a human, and you know all humans are making mistakes. Okay, there are some examples. Maybe one remember the AS7007 incident, or there was 2 years ago something with YouTube in Pakistan where a configuration mistake in the global BGP routing infrastructure just leads that YouTube wasn't available for some hours.
So actually Pakistan announced the prefix of YouTube with a smaller subnet or prefix and routed it to a black hole because they wanted to not allow the connection to YouTube from Pakistan anymore because some illegal content from Pakistan was hosted there, so they didn't want to reach their people YouTube anymore, and so they just announced it in the BGP, the routes there, and this was propagated beyond the borders of the country for sure, and this was because YouTube was not reachable. And if you look at the YANA site, for example, you can really see how the routing tables are flapping because YouTube announced it back with a smaller subnet, so they can be reachable again.
So, okay, that means if you, for one, part of this global BGP community, you can nearly announce every route you want. There is some kind of route filtering, but on a global scale, on a central node in the internet, you can't filter all these routing entries. So maybe you've heard of the, what was Last Hope? I think last Hope there was something with a global BGP man-in-the-middle situation set up. Ask me later if you're interested. Okay, so BGP got some security mechanisms which are, as I said, not based in the BGP protocol itself, but they're given over to TCP, which means BGP uses the generic TCP MD5 signature option, which is defined in the RFC 2385. And suddenly you will just think, okay, yes, MD5. I've heard about MD5 on the last CCC. No, okay, but MD5 isn't really a good hashing algorithm. That's, in this case, not the main problem, so you can't just assume the MD5 hash because you don't know the secret password configured to secure MD5. But MD5 is calculated on a modern laptop in, I don't know, in like nothing. Okay, but they're working on it. So there is a working group of the IETF which just throw out some drafts which will extend these TCP security option. Okay, so but consider for yourself, does this really add a security value? Both operators has to configure the same key, and that's the point where everything breaks off normally. So, okay, something is wrong with BGP. Oh no, our routing is not working, so let's just, to be sure, let's remove the secret keys for first, and then have a look deeper into the configuration. Okay. So, you see, there is a security mechanism, but with our side, we were on some big customer sites, there is nearly nowhere used.
The problem is also with the MD5 key that you need a process to change these keys. And in the moment where you change a key on one side, you also have to change on the other side. If not, your PGP session falls down and the routes are removed from the table.
Okay, so far for BGP in general. Now we'll come to the first fun part. This is one of the meat slides. We got some tools coded in early this year. One of this is the BGP CLI, which is a command line interface for the BGP routing protocol, so you can manually establish BGP sessions and propagate some update statements with whatever you want. You can actually brute force live MD5 keys, but this is more like a log file generator. So you won't use this actually, but use the second tool, which is the BGP MD5 crack. You will see live now. Okay. First of all, I will make this a little bigger.
Thing is, if you can crack it offline, because you have already a hash in the packet, so can crack it offline with a C program, which is much more efficient than cracking it over the network. We are live connection, which will all be sent over the network, generate logs, and it's not even that fast. So there is no point in doing that. You just sniff it and let it crack offline on your laptop. All the demos assume that you are in the core of the that you are in the network of a provider. So there's normally in all these networks there's a trusted core assumed, but
I'm not going to allow you in my core.
Sorry?
I'm not going to allow the two of you in my core.
Yeah, that's true, but
that's good for you. So, okay,
for sure.
Just to get on with the demo, we got a PE router here, which got a global routing table looking like this. So we got some C routes which are directly connected. We got one OSPF route, but the main part is we got no BGP route. So in the next step, I will just take my notes. And, whoa. So, and launch the BGP CLI. And I just have to configure some session parameters, which means, okay, I'm going to propagate autonomous system 2, and I have an idle time of 8 seconds, which is just for demo purposes a really short time. Okay, after that, I'm going to establish my BGP connection. So I'm connecting to a peer. I have to say, okay, I need to be configured as a peer on this, on the other side too. So, but this means you just need to get into the position of a valid peer. Either you can do this by hard spoofing the wire or by doing something like, I don't know, ARP spoofing or stuff like that. We are not talking about how to get into the core, but what you can do once you are in the core. Okay, so I got an BGP session up and running. So you see the PE just logs, okay, I got a new neighbor up. And after that, I can build some BGP update statement with this statement, and it just says, okay, hello, I'm the next hop for some new network. So once I send this out with the update command, you can see on the other side a new BGP route appearing, which is just this network, and the next hop is my laptop. Okay. Seems to be really easy, doesn't it? So we're going to make this a little bit harder. So I'm changing to be another peer now, and this peer is secured by an MD5 shared secret on both sides. So you will see this peer disappears, and if I try to connect to this peer like I did to the other one, this won't work. So we get a timeouted connection, and on the other side, we got a log message, okay, bad digest or no MD5 digest from this peer. This is because all my TCP SYN packets to the BGP port are not MD5 signed, so the router just drops them. Okay, but in the other way, the router sends me TCP SYNs too, which means I can just sniff one of these SYN packages and run a brute force attack against. So that's what I'm going to do. Okay. You can either run this attack against a live interface or against a PCAP file. For the demo, I will use the PCAP file because this is hell more reliable. And this PCAP file just includes one TCP MD5 signed SYN packet, and you will see after 6.2 seconds, we found out of a word list with 4 million entries the right password. This means, okay, MD5 is really short to generate. You don't need much CPU power, and you can even do real brute force if you get some hardware tweaks. Okay, but this shows, okay, your MD5 secret is not unbreakable. Okay, once I got this secret, I can do the following, configuring this secret in the BGP CLI for that peer. After that, setting up the session again and connecting to this peer. You see there is no more timeout appearing. Instead, we got a real neighbor up and running. And again, we are connected. We got a connected BGP session. After that, we can insert whatever we want into the BGP routing process. So building the update statement again, sending an update, and we got a new routing entry. This time, our other host is the next hop, but we got routing entry into the globing routing table of this router. Okay, so that are these for short. You can do a lot of other nasty stuff. You can withdraw on some other routes. You can insert, I don't know, some crazy routes, some malicious BGP statements, like something with an AS path of 255 entries, stuff like that. Okay, so,
Question.
yeah. Okay.
Have you looked into any kind of buffer overflows and code execution vulnerabilities through the BGP session
We
connection?
haven't searched for that. We're
right.
just focusing on BGP is just the main part. We need BGP in another context to insert something into the MPLS stuff, but you will see later on. So it was just the basic to write these tools.
Yeah.
We didn't do any more research into BGP itself because its implementation, it depends on the implementation, if it's a Cisco device or Juniper or whatever. We saw something other. We saw some main problem with the design.
Yep. Thanks.
Okay. So please wait till the end. We need to go on because we don't got much time. So for completeness, this is what we found in an audit in a big 40K user backbone. We find this configured BGP MD5 key and decoded. It's just like Cisco, the default of the configuration manual. So they want to make it secure, but actually they didn't add any security at all. Okay, so I will hand over to Simon. He will tell something about MPLS in general.
Okay, thanks. MPLS is a technology defined in RFC 3031 and is used to in provider backbones for labeling traffic to different sites, for example, and it's made for forwarding, and it's for performance reasons. You don't have a normal routing table like for IP. You don't have to route RTP packets. You can just route packets based on their MPLS label, which are 20-bit and so easily machine in hardware readable, and you don't need explicit software. And it's deployed in most carrier backbones. Also, it's used by many big enterprises to route in between their corporate networks, between their locations. You have different technologies. Some are called, the ones called layer 2 VPNs or layer 3 VPNs. In the layer 3 VPNs, you have IP routed infrastructure. So your core is IP-based. In a layer 2 VPN, you can also have a core which is based on Ethernet, so you are forwarding directly Ethernet packets, or everything what's about Ethernet. And yeah, there are different terminologies for layer 2 and layer 3 VPNs. For this kind of talk, we will just call it layer 2 VPNs or layer 3 VPNs for the difference.
Okay, so an MPLS is used in almost every big provider backbone in the world. Okay, there are some kind of layer 3 VPNs where you're selling some kind of VPN service, and this is comparable to frame relay or ATM and stuff like that. It's highly virtualized. So you got a shared infrastructure, you got virtual separated routing processes on your PE routers, and additionally MPLS labels. So MPLS is used for forwarding on the one side, but it's used for client separation for the actually VPN service on the other side. So it's very flexible with the VPN topologies you want to build up. So you can do any-to-any topology, or you can set up some hub-spoke topologies, and nearly everything you can imagine in a VPN context. Okay, just to get you into the terminology. Okay. On this side, you got a provider backbone, which is just for forwarding purposes, and you got the VPN sides, which is the customer network. So you got a provider network. Inside the provider network, there are called P routers. BGP routers are just backbone routers in the ISP's backbone, which are strictly doing forwarding. They have nothing to do with the client side. They are only connected to the provider backbone, and they only know internal provider backbone routes. They don't know any shit about these client sides. So then there are the PE routers, the provider edges. These edges are actually doing the traffic separation. They do the initial traffic labeling, the traffic classification. So if the customer sends in some traffic, the PE router puts a sticker on it. Okay, this is red traffic. It has to go to the other side of the cloud. After that, MPLS is used for forwarding the traffic to the other PE router, which sees, okay, there is a red sticker on the traffic. This must be for customer side A. Okay, so you got the customer sides, and in the customer side you got some CE routers, which are mainly for exchanging customer routes, because your provider backbone also is used for transporting all the client routing information stuff. Okay, so it could be that there are more than one label in transport. There could be one label for, okay, this packet has to go to this PE router. Then there could be another label which says, okay, it should use this traffic path. And then there could a third label which says, okay, and it's traffic for customer VPN A. So there could be some more labels than only one MPLS label on the traffic. Okay. On the other side, you can have more than one customer side connected to your PE router, which means you got one customer green and one customer, say, red. It isn't red, but I don't care. Then you need on your router side something called VRF, or Virtual Routing and Forwarding Instance, which means you get something like a virtual router on the router itself. So you get for each client a virtual routing instance, and this is absolutely needed because you shouldn't mix up customer routes with your global routing table, which just includes backbone routing information. And on the other hand, you shouldn't mix up routing information from two different customers. So, but because you got these virtual routing and forwarding instances, it's absolutely possible that two different customers can use the same IP address space. So you can have a 10.2 square something network in a green VPN, and you can have the same network in another VPN. Your backbone don't give a shit about the actual used IP address because it's only forwarding on MPLS traffic information. Okay. By the way, inside your backbone network, you will speak multi-protocol, BGP, to share the customer routes and stuff like that. Okay. We're short in time. I will skip this. If you're interested, just come to our workshop. So, one, for the trust model of MPLS, it's absolutely necessary that you got a trusted core assumed. Once an attacker is in the trusted core, it breaks your security model. If I'm inside your MPLS core, I can do nearly everything I want. You will see. But this means by the design of the technology, there is no attack from outside the core possible. Because outside the core is only a customer network, and this will be forwarded transparently. But there are no additional security controls available. So you can't say, okay, please secure this MPLS VPN with that key, something like that. That means if you're a customer of such an MPLS VPN, you can only trust your provider, or, okay, there is something in the MPLS context. Is another routing protocol. No, it's not a routing protocol. It's LDP, the Label Distribution Protocol, which you can secure with MD5 too. But, okay, you've seen MD5. okay, do some brute forcing stuff and get the key. So on the other hand, this LDP only is spoken inside your trusted core. So why should you secure a protocol spoken inside a trusted core? In a core with no attacker inside, there is no real threat model for this. Okay, but this leads into some really grim debates between Corp Global Network Team and Corporate Information Security. Because network team says, okay, yeah, it's MPLS, it's fine, just trust the provider, throw packets in, get packets out. But the InfoSec team says, okay, and what is with the
confidentiality, and is there some encryption in place, and why it's called VPN? Okay, it's called VPN, it's virtual private network, but it has nothing to do with encryption or something like that. So if you say MPLS VPN, you will never have encryption if you don't have other mechanisms in place, for example, speaking IPsec or something like that over the MPLS.
Yeah. Okay, so there are some words out of the bullshit bingo which appears directly here. If you go to your network team and say, okay, what is with an attack from inside the MPLS network? You'll say, okay, come on, nobody will ever try this. Or, oh, come on, you're paranoid. Just trust your provider. So, okay, for a long time, all these attacks were only theoretically. Now, we invented a tool, it's called MPLS Redirect. It's just a proof of concept for attacks on MPLS. It assumes that the attacker is inside the trusted core. So again, we don't talk about how to get into the core, we talk about what to do once you are in the core. It's a short command line tool, and it modifies the VPN labels of your MPLS traffic. So it redirects traffic from one customer side to a different customer's side. Okay, we will have a short demo for this again. First of all, that's our setup. We got, oh wait. Okay, sorry for that. But we plan to present with the other notebook, so I could do this not on the Beamer. So, okay, that's it. Again, we got two different VPNs. We called, okay, we're in Holland, so we called the one beer and another one spliff. And we will show you, you see they got both the same IP address spaces. This is the 113, this is the 112 network. And we will demonstrate that it works like it should, that you can ping from this VPN side a notebook in the other VPN side. So, which means to, because we got enough devices, I will use the virtual PE on the one side and ping Simon's notebook in the other network. So just, okay. So he is in the red VPN, and I go to ping him in a red user context. This should be your address. So, okay, this is working. I did a ping from the red customers, virtual routing and forwarding, to the network on the other side, and it's success. You can even see in the Wireshark all the packages, they're wearing an MPLS label. So if I try to ping out of the context of the green customer, this ping will time out.
The green customer in this demo has the same IP address space, but my box actually is connected via the red, so it's not reachable because I'm on the other side. But
so the next thing is that I need to set up my redirecting tool. For this, I need the VPN labels, which are actually shown by this command, which is the 1917. So where are my shells?
the VPN labels itself can also read via, if you are in the core, you can read them in Wireshark or your tool of choice for network sniffing, and see there the labels too. So you don't need access to an actual CLI from, for example, from a Cisco device to look at the labels. The labels are transmitted.
So, and if I don't type the labels wrong, which could happen, maybe didn't get much sleep this night, we should now, with both tool instances in place, be able to ping the system in the red VPN, but on the other side, in the green VPN too. So, which means...
And I'm still on the red customer side, so my port didn't change anything.
Yeah, he's still connected to this side, which means, okay, we showed you a ping from red to red is working. Ping from red to green, time's out. So after putting some, mixing up beer with spliff may end up in some kind of unresponsiveness. After you put some magic into this box, which are actually my two tool instances, we are able to ping from the red customer side into the green VPN. So, again, maybe you can stop the tools for a while, and you will see pinging from red to red works. Ping from red to green ends up in a timeout. There is no device connected to the green VPN side. So I will launch up the tools again. They're just in the data path manipulating the MPLS labels, and after that I can ping in the red VPN context, but I can ping the same device in the green VPN context too. So this means once I'm inside your MPLS core, I can move traffic from site A to site B, maybe pop up a new site C and get traffic out of that, and okay, just think about. I heard it's some kind of thing called applause after a demo worked. Thank you. So, what does this mean? Okay, I can, as an attacker inside your MPLS core, I can just spoof every system in your network I want. So I can just set up a fails routing entry, which says, okay, this square 32 network, this host is now located in a new VPN, so maybe it's your DNS server, it's your central authorization portal, stuff like that. Maybe it's your LDAP, or just use your imagine. But we not only can relabel existing traffic, which means we had to be a valid customer, but we can also insert traffic. This is another tool. It's called MPLS TON. It again assumes that we are inside the traffic path and inside the core, and this tool just puts on a virtual tunnel interface and label every traffic that comes into this tunnel interface with a given MPLS label. And it also works bidirectional, which means, okay, every traffic arriving from the MPLS cloud labeled for this customer VPN is popped off the cable and thrown into the tunnel interface. So we are now able to put up a virtual interface on my local box, which is part of one given MPLS VPN. It's only tested with Linux so far, but the tunnel API should work on other systems too. So now an attacker has an MPLS VPN-enabled network stack, which means, okay, just sit one time in the cloud and insert traffic in every customer VPN you want. So, okay, we will have a demo for this too. Okay, so this is the tunnel tool. Where is my... this one? Please, no, there it is. Okay, so I just launch up the tool, which now is configured for the other side. Okay. So I just launched up the tunnel interface in the mode, okay, you will be a layer 3 VPN, not a layer 2 VPN. You're working on this incoming and outgoing device. You're using these incoming and this outgoing MPLS label, and you also use this to incoming and outgoing MAC addresses. So after that, you will see I got a new interface on my notebook. Now I will just apply some stuff to this interface. So I will assign an IP address. I take the MTU down because we have to add the MPLS label. And after that, I append some route to this interface. So now, from inside the MPLS core, got an interface connected to the green customer VPN, which his notebook is also connected to, and I'm now able to ping from inside the MPLS core the outside customer's VPN side. And you see, this is, I get response. This is actually bidirectional. I can do stuff like, okay, do an nmap inside this customer side. Maybe there is some interesting internal authentication system which I want to scan. And okay, we're running out of time. But you see, I can be part of a customer side just with creating a virtual tunnel interface. So what are your chances? What are your mitigating controls? First, okay, trust your carrier. If your carrier says, I got a trusted core, which, by the way, every carrier will say, then you're fine. On the other side, contractual controls might kick in. If you're bound to some contractual stuff, you can't just say, okay, I will trust my carrier. You have to ensure that all your traffic is secured. And this means, okay, you have to either authenticate everything. This traffic is really from that side, or you have to implement some special borders of trust, in this case, layer 3 devices that do some, let's say, IPsec over the MPLS cloud. That's the only chance.
The problem with the trusted core is also that until the PE devices and the P devices are all in the hand of the provider, and there is no way to connect to it, then you can maybe assume a trusted core, but what is if the PE is at the customer side, it's on the customer's control, yes, the ability to change also not the transport labels, or also the labels back in the backbone, and can so maybe more than one customer terminates on one PE device, and if you give the PE device out of hand, maybe you don't do that, but in the end you are in the core, and you have cables to the core, and this is the most biggest probability where you can access such a core, and we did an evaluation of where we asked different MPLS providers if they would give us the PE device under our control, and about 60 to 80% answered with yes, which you can assume, okay, every other customer maybe has some PE device, and then there is your trust to the core.
Okay. Okay, if you think it's secure enough, we're fine. We're running out of time, so I have to go on quickly. Our last technology we want to discuss is called Metro Ethernet. It's just booming by the time, and it uses different technologies. We're gonna talk about the Ethernet over MPLS, or so-called virtual private lines. And this means
just imagine it as an Ethernet plug, which is connected to all your sites and over a switch, but it goes all over the MPLS backbone, and the provider serves that service for you.
Yeah, so you can also, instead of forwarding layer 3 IP packets over your MPLS backbone, you also can forward layer 2 Ethernet frames. And this is actually what Ethernet over MPLS does. It's just like a big virtual cable. It's like you're throwing an Ethernet cable from Amsterdam to, I don't know, Brussels or to New York. So, but this definitely changed your trust model. If you got a layer 3 VPN, you get some border of trust. You get your layer 3 device, which does actually routing. But now you include the whole carrier network into your zone of trust, and because you're forwarding layer 2 frames, you don't got the routing process anymore. So with this different zone of trust, there might be existing threats that get a new scope. So think about Ethernet-based attacks that come over the cloud, or misconfiguration will have a much larger impact. Think about some VTP-speaking device which is configured with a very high revision number and not set to mode transparent and just connected to the MPLS extended layer 2 local Ethernet. No, not local, global Ethernet, stuff like that. But there might also new threats showing up. Something like your, skip this. But one of the main threats is that there are some traditional Ethernet-based attacks that are now able to run over the cloud. So if you're sitting in Brussels and got an Ethernet over MPLS tunnel to your site in Amsterdam, you're able to do some kind of layer 2 attacks. Think about the spanning tree route of both sides sitting in one. You can do layer 2 based attack. We've tested this with Yersinia. Actually, most of the Yersinia attacks, like they work. If they work, they work. Also over the cloud. And you can do something like ARP spoofing from Brussels to the site in Amsterdam. So ARP spoofing isn't anymore a local problem, but it's a global problem. You can now force traffic to leave your site in Amsterdam. Okay, so MPLS TON, the tool, also can build up a layer 2 endpoint. This means we can also take part of the layer 2 network. We don't get a demo for this, and for completeness, we also coded an LDP, command line interface. LDP is a label distribution protocol which is needed for propagate LDP information about layer 2 VPN endpoints. Okay, so short wrap up on carrier Ethernet. It's a really interesting approach. Think about you got some crazy vendor-dependent protocol which actually need layer 2 to work. You can now extend your site by layer 2 from Brussels to Amsterdam. But it changed your whole trust model of Ethernet. Ethernet, till this technology, was a local problem. You get something like, physical security against it. Now, physical security isn't actually something you can do against these attacks. Okay, we wanted to save the best for the best for last, which, from the bingo again, nobody will ever try to do this. It's insert into multi-protocol BGP, which means we are not inserting IP routing information anymore, but inserting customer VPN information into your BGP process. Got 7 minutes left, so maybe I can show this demo, hopefully. Okay, we'll skip this demo. If someone is interested in it, we will have a large workshop after. So, summary and outlook. There are some technologies used in backbones that are got kind of debatable trust model, and so you need some new security controls to work against these threats. Okay, and we just want to make you intent of these problems. So be aware, MPLS isn't just some magic that just works. It can break too. Always think about a trusted core is assumed. It's that simple. Okay, some final wisdom, as RFC 1925 says, read for yourself, and if you're really interested in your stuff, just get your hands on some devices and test that shit. Okay, this actually leads me to the next thing. We've planned a little workshop with our MPLS lab. We got some more devices to build up a big backbone. We'll hold in Village Fubar, or maybe we will find a better location. I don't know how much people are interested in. We'll start in around half an hour, and it's open-end, so join the whole night. And please bring your devices. Bring MPLS-capable devices. Okay, so there's never time enough. We hurried up. You got 5 minutes for questions.
At last we have a little bit less, so 1 or 2 questions, because you guys are always there.
Yeah.
So
right.
1 or 2 questions, please. Oh.
Okay, so maybe I missed it because I had to step out to take a call for a moment. But you guys promised to say something, or you said the design is wrong. I think you were talking about BGP at the moment. So what is the right design?
It's not about a wrong and a right design. It's just about the design assumes the core is trusted. That's the point. If you got a trusted core, you're fine. If you don't get a trusted core, you got all these problems. It's that simple. It's not a big design clue, as you said, okay, I can break you all the time. It's just, if you got a trusted core, you're perfect. Absolutely fine. But if not...
Okay, one last short question, please.
If you do not fully trust your core, that means you have to run IPsec or